ECC with simple math. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today, we're going to demystify the two core applications of elliptic curve cryptography: the ECDH key exchange and the ECDSA digital signature algorithm. The math behind ECC can seem intimidating, so we're going to strip it down to its essentials. We will use a simple, custom-defined elliptic curve and small prime numbers to walk through every step of the process. By the end, you will see exactly how the math works and gain a much deeper intuition for how these powerful protocols provide security. Recap: the core idea of ECC. Let's quickly recap the fundamental principle of ECC. Everything is based on the idea of point multiplication on an elliptic curve, which is a trapdoor function. It's easy to take a public starting point G, and a secret number D, and calculate the final point Q by adding G to itself D times. However, it's computationally impossible for someone who only knows G and Q to figure out the secret number D. This relationship is the basis of our key pair. D is our private key, and the final point Q is our public key. Our toy example: the domain parameters. To make the math followable, we must first define the public rules of the game, or the domain parameters. For all the examples in this presentation, we will use the simple curve defined by the equation y squared equals x cubed plus 2x plus 2. We will also perform all our math in a finite field, using a small prime number, p equals 17. This means any result is always taken modulo 17. Our public starting point, or generator, will be the point G equals 5, 1. Finally, the order of the subgroup generated by G is n equals 19. This means that our private keys and nonces must be numbers between 1 and 18. These public parameters are the shared foundation for all our calculations. Our lookup table of points. To make our examples easier, I've pre-calculated the results of multiplying our generator point G by different numbers. This is our lookup table. For example, 2 times G is the point 6, 3. 4 times G is the point 3, 1. You can see that multiplying G by different numbers results in different points on our curve. In the real world, there's no lookup table. These calculations are performed on the fly with astronomically large numbers. But for our learning purposes, this table will let us focus on the protocol logic instead of the point addition arithmetic. ECDH key exchange. First, let's explore the elliptic curve Diffie-Hellman protocol, or ECDH. Its one and only job is to allow two parties, Alice and Bob, to agree on a shared secret value over a completely public and insecure channel. It is a key agreement protocol, not an encryption algorithm. The secret they generate at the end of the process is then used to derive a key for a fast symmetric cipher, like AES, which handles the actual data encryption. ECDH solves the critical problem of how to get that shared key established in the first place. ECDH example. Step 1: the secrets. Let's begin our example. Alice and Bob both know the public domain parameters, including our generator point G, 5, 1. The first step is for each of them to invent their own secret. Alice generates a random number to be her private key. Let's say she chooses A equals 4. Bob does the same and chooses his private key, B equals 7. These numbers are their ultimate secrets. They must never be transmitted or revealed to anyone. Their entire goal is to use these secret numbers to arrive at a third, shared secret without ever exposing their original ones. ECDH example. Step 2: the public keys. Now, Alice and Bob each use their private key to generate a corresponding public key. This is done by multiplying their private key with the public generator point G. Alice computes her public key, A, by calculating 4 times G. Looking at our lookup table, we see that 4 times G equals 3, 1. This point is Alice's public key. Bob does the same with his private key, 7. He computes his public key, B, by calculating 7 times G. Our lookup table shows that 7 times G equals 0,6. This point is Bob's public key. These public keys, A and B, are not secret and can be exchanged openly. ECDH example. Step 3. The exchange. Alice and Bob now exchange their public keys over the insecure network. Alice sends her public key, the point A, 3,1, to Bob. Bob sends his public key, the point B, 0,6, to Alice. An eavesdropper, Eve, can see everything that is exchanged. The generator G, Alice's public key A, and Bob's public key B. However, because of the ECDLP trapdoor, she cannot use this information to figure out Alice's secret number 4 or Bob's secret number 7. She is stuck. ECDH example. Step 4. The shared secret. This is the final, magical step. Alice takes the public key she received from Bob, B, and multiplies it by her own private key, A equals 4. Her calculation is 4 times B, which is 4 times open parenthesis 7 times G close parenthesis. This results in 28 times G. Since our group has an order of 19, this is equivalent to open parenthesis 28 modulo 19 close parenthesis times G, which is 9 times G. Looking at our table, 9 times G is the point open parenthesis 7,6 close parenthesis. Meanwhile, Bob takes Alice's public key, A, and multiplies it by his private key, B equals 7. His calculation is 7 times A, which is 7 times open parenthesis 4 times G close parenthesis. This also results in 28 times G, or 9 times G, the point open parenthesis 7,6 close parenthesis. They have both independently arrived at the exact same point. The x-coordinate of this point, 7, is their shared secret. ECDH summary. Let's recap what just happened. Alice and Bob started with their own private numbers and, by exchanging public points on a curve, were able to compute a final, shared secret point. An eavesdropper who saw all the public information was unable to compute this secret because she was missing the private keys. The x-coordinate of this final point can now be used as a high-entropy shared secret, which is typically then hashed to produce a symmetric encryption key. This elegant process is the foundation of almost every modern secure handshake on the Internet. ECDSA digital signatures. Now, let's explore the second major application of ECC, the elliptic curve digital signature algorithm, or ECDSA. A digital signature's purpose is to prove that a message came from a specific person and has not been altered. It provides two critical properties: authenticity, which verifies the sender's identity, and integrity, which ensures the message has not been tampered with. It is the cryptographic equivalent of a real-world, tamper-proof signature. ECDSA example. Step 1. The setup. Let's set the stage for our signature example. Alice wants to sign a message. For this, she will use her private key from our previous example, D_ equals 4, and her corresponding public key Q_ equals 3,1. The first step is to hash the message to produce a fixed size number. To keep our example simple, we will pretend the result of this hash is the number Z equals 6. Finally, and this is a critical step, Alice must generate a new, secret, random number to use as a nonce for this signature only. Let's say she generates K equals 3. ECDSA example. Step 2. Creating the signature R. The signature has two parts, R and S. The first part, R, is derived from our random nonce, K. Alice takes the generator point G and multiplies it by her nonce K. In our case, this is 3 times G. Looking at our table, we see that 3 times G is the point 10,6. The value of R is simply the x-coordinate of this point, taken modulo the group order n. So, R equals 10 mod 19, which is 10. The first half of our signature is complete. R equals 10. ECDSA example. Creating the signature S. The second part of the signature, S, is where the private key and message hash come in. The formula is S equals K inverse times, open parenthesis, Z plus R times D sub A, close parenthesis, modulo N. Let's plug in our numbers. K equals 3, Z equals 6, R equals 10, and Alice's private key D sub A equals 4. First, we need the modular inverse of K, which is 3 inverse modulo 19. A little trial and error shows that 3 times 13 equals 39, and 39 modulo 19 equals 1. So, K inverse equals 13. Now we calculate the part in the parentheses. 6 plus 10 times 4 equals 46. 46 modulo 19 equals 8. Finally, we multiply. S equals 13 times 8 modulo 19, which equals 104 modulo 19, which equals 9. So, the second half of our signature is S equals 9. Alice's full signature is the pair R, S, which equals 10, 9. ECDSA example. Step 4, sending the message. Alice has now successfully signed her message. She sends 3 pieces of information to Bob across the public network. The original message itself, the R component of her signature, 10, and the S component of her signature, 9. Bob, or anyone else, can now use this information along with Alice's public key to verify that the signature is authentic. Notice that Alice's private key DA equal 4 and her secret nonce K equal 3 were used in the calculation, but never transmitted. ECDSA example step 5 verification math. Now we get to the verification, which has its own set of calculations. Bob receives the message, hashes it to get Z equals 6, and receives the signature R equals 10, S equals 9. He also knows Alice's public key Q sub A equals 3, 1. First, Bob calculates the modular inverse of S, which is 9 to the power of negative 1 modulo 19. Since 9 times 2 equals 18 is congruent to negative 1, then 9 times negative 2 is congruent to 1, and negative 2 is congruent to 17 modulo 19. So S to the power of negative 1 equals 17. Next, he calculates 2 intermediate values, U1 and U2. U1 equals Z times S to the power of negative 1 equals 6 times 17 equals 102, and 102 modulo 19 equals 7. U2 equals R times S to the power of negative 1 equals 10 times 17 equals 170, and 170 modulo 19 equals 18. So Bob has U1 equals 7 and U2 equals 18. ECDSA example. Step, the final check. This is the final verification step where everything comes together. Bob uses the values he just calculated to find a point on the curve. The formula is P equals U1G plus U2Q sub A. Plugging in our numbers, we get P equals 7G plus 18Q sub A. Since we know Alice's public key Q sub A is just 4G, we can substitute that in. P equals 7G plus 18 times 4G. This becomes 7G plus 72G, which is 79G. We take this modulo our group order of 19. 79 modulo 19 equals 3. So, Bob is really calculating the point P equals 3G looking at our lookup table. 3G is the point 10, 6. The final check is simple. Bob takes the x-coordinate of his calculated point, which is 10, and compares it to the R value he received from Alice, which was also 10. They match. The signature is valid. Why did that work? The verification math seems almost magical, but it works because of how S was constructed. A deep dive into the math is beyond the scope of this presentation, but at a high level, the verification formula is essentially a clever algebraic rearrangement of the signing formula. It is designed in such a way that if, and only if, the signature was created with the private key that corresponds to the public key used in the verification, will the final x-coordinate equal the original R value. Any change to the message or any attempt to forge a signature with the wrong key will cause the final check to fail. Conclusion. The power of ECC. Today we've demystified the two main uses of ECC by walking through the math with simple, concrete examples. We saw how ECDH allows two parties to use point multiplication to create a shared secret out of thin air, providing the foundation for confidentiality. We also saw how ECDSA uses a combination of a private key and a secret nonce to create a signature that can be publicly verified, providing authenticity and integrity. While the real-world numbers are astronomically large, the core principles you saw today are exactly the same. This elegant and efficient mathematics is what secures our digital lives. Final thoughts. By breaking down the math into small, manageable steps, we can see that ECC is not magic, but rather a very clever application of well-defined mathematical properties. Understanding these fundamentals is key to appreciating why ECC is so central to modern security and why concepts like keeping private keys and nonces secret are so critically important. I hope this detailed walkthrough has given you a much clearer picture of how these amazing algorithms work. Thank you for your attendance. Please consider subscribing to the channel.